Good afternoon, everybody. I'm Neeti Pokhriyal. I'm a doctoral candidate at the Department of Computer Science and Engineering, SUNY Buffalo. Today, I'm going to present my work on poverty mapping. So what is the problem? The problem we are trying to solve is we want to produce spatially detailed policy-level poverty maps that are diagnostic, cost-effective, can be produced frequently, and ensures coverage of an entire country. So what is poverty mapping? Poverty mapping refers to spatial representation of poverty values across a country. What is needed in ideal conditions is we need a poverty map that is available at the finest level of policy planning, and also maps that are decomposed or disaggregated based on various factors like gender or ethnicity or urban-rural, so that targeted policies can be made for interventions. Currently, poverty maps are created using human and time-intensive intensive household detailed surveys, which are either household surveys, and they require a lot of monetary effort. They also lag considerably for sub-Saharan Africa. So by the time you have a poverty map, you collect the data and you get the map, you already have a lag of 3 to 5 years. The country in this study is Senegal, which is a sub-Saharan West African country, where more than 52%, more than half of the population lives in poverty. And just giving you another statistic about that country is it has per 100 people there are 98.8 mobile phone subscriptions. So that motivated this work is that can we exploit this mobile connectivity, mobile accessibility to target poverty. I will describe the data sets that are used in this study. We use the call data records, which is a record of mobile phones. So when we use phones, we have the precise location of where the phone was used and who called whom. The data is, we have 11 billion records corresponding to 9.4 million subscribers from Sonatel, Senegal, which is the predominant telecommunication provider in that country. Just to give a perspective, the data spans the entire year of 2013. The population of Senegal for 2013 was 14 million. Then, based on our collaboration with the National Statistics Office at Senegal, I have access to the concurrent 2013 census data. 10% of the census data is spanning 1.4 million individuals and 150,000 households. The additional data that is used in this study is a multidimensional poverty index that it complements the income or consumption-based poverty, and it measures concurrent deprivations that an individual faces in the 3 critical indicators. One is education, health, and standard of living. So if you put poverty mapping in a computational perspective, it brings to light a lot of challenges. One is, how do we learn from these heterogeneous sources of data which capture different aspects of people and space? So CDRs give us important information of mobility of a person, whereas census gives me somewhat detailed information of a household and an individual, and the MPI data gives me a course level expert information on poverty. This brings the second challenge, which is that the data has varied spatial and temporal granularity. So what is the need? The need is to build novel algorithms that can learn from these big data sets, for example, the CDRs, along with focused small data sets like census and the poverty index. And also, if we want to institutionalize these changes for, so that they have, they work on the ground, we need to build human interpretable methodologies so that we can convince the policymakers. The contributions of my work has been two. So first, I described two approaches to generate policy planning level poverty maps. So in first approach, I use the CDR data and have a graph theoretic formulation of the information accessibility at each spatial location and use it to generate maps. I will discuss it in the next slide. In the second approach, I use the call data records and extract behavioral indicators or metadata statistics from them to characterize the macro level patterns, and using this generate an alternative poverty map. The second approach, I just don't stop at displaying the poverty maps, but go a step further to know that do such big data like CDRs have the capability to predict individual deprivations or individual indicators of poverty. Some of the indicators that I studied are deprivation in education, water, sanitation, electricity, etc. I provide qualitative validation based on our discussion with the National Statistics Office at Senegal. And because one of the challenges is lack of ground truth data, I use the census data that is available to quantitatively validate the maps that I generate. So this is the first approach, the graph theoretic approach, where this is I call it virtual network, and this is the virtual network abstracted at a regional level for Senegal. Senegal has 14 regions. Each node is a regional centroid. Two nodes are connected if there was a call or text exchange between these two nodes. This is a undirected weighted graph. The edges are weighted corresponding to the volume of calls and texts exchanged. Now, with this graph, I need to quantify the information accessibility at each node. So I define a metric for that. So the metric is such that regions that have good accessibility, they get high accessibility to information. And then if what I have overlaid on this map is the current poverty map of Senegal. An interesting observations come to light is that regions that have good access to information are less poor, and the regions that are poor look isolated on the map. So the dark regions are poorer than the lighter regions. Using this, we learn a regression model which helps to predict poverty at any spatial location, and this is using this we predict poverty at the finest location of policy planning, which in Senegal is called the commune. And these results are validated using the census data. Now I'll come to the results. This is the existing map. These are the maps that are produced for Senegal at 512 the communes, and you see that there is heterogeneity between the regions. When I compare this with the actual poverty values calculated from the census data, so I would like to point out that at commune level we get a correlation of 0.85, which means that CDRs have the capability to generate detailed poverty maps. Since poverty is studied and exhibited differently for urban and rural, this was the map for rural. This is the map for urban areas and also predominantly urban communes. This is the second approach where using the behavioral indicators extracted from call data records, I want to see how they can predict the individual indicators of poverty. So first the individuals are localized to the communes, and then we learn in a multitask learning framework, because we have a number of behavioral indicators on one side and we have a number of targets on the other side. And we see that some of the indicators of poverty, like deprivation in electricity and cooking fuel, are even acid, can be predicted for, very accurately. And these are again cross-validated using census. I'll be happy to talk about the model and how they're validated later on. Just to conclude, so our methodology gives does generate accurate spatially detailed poverty maps that can be generated frequently at low cost and complementation to traditional census. And we also disaggregate to individual indicators of poverty. These are advantages even to countries which, where even census cannot reach, which are in conflict or very remote areas. In future, I am working to combine this with other heterogeneous sources of data like remote sensing and satellite imagery to generate further maps. Also, it is interesting to study how can we decompose it to subpopulations which are traditionally vulnerable to poverty, like women and children. And I am also looking into understanding the bias and uncertainty in different heterogeneous sources of data. And can we infer poverty for the population that is not represented in the data? I have a poster outside. Thank you.